Okay, so as you saw on the screen, your heating curve graph should look like this. You should see 5 straight lines, straight-ish. They should be straight enough based on how your graph looks. Okay, now no graph is perfect, but in general, you should at least see 2 very straight lines, and that's this flat one here, this flat one up here. The other 3, I think, should be, for the most part, straight. If they are not straight on your graphs, try to make them straight, okay? So in your notes, make sure that you have the heating curve that looks just like this, okay? The little boxes I'm going to erase as we go along, and make sure that you're adding this to your notes, okay? Great. So if we look at our axis, or we look at a graph, temperature is on the y-axis. I know that you have -30 down here, and you never used it. That's okay. You're just given a range of temperatures, and the time goes from 0 to 20 minutes. I know you ended a little after 18 minutes, but that's okay. You can keep it to 20, no big deal. And so in our graph, what we're seeing is that as you heat something up, the longer you heat something up, the higher the temperature gets. But at 2 points it flat lines. It's kind of weird. So the whole point of this video is to kind of talk you through what's going on with all 5 parts of this heating curve. So the first part is here. So in the video you watched, when you started, you saw a bunch of ice cubes that were being heated up. So my first part is going to be this first positive slope right here. So in your notes, make sure that we're writing down what that indicates. So based on how large or small your graph is, you may need to draw some arrows. So what this means for all heating curves, it's not just of water, it can be any heating curve of any substance. All right, that's pretty important, any heating curve. So for water, what we're seeing here is that this first part is a solid heating up. Now, obviously, solid water is ice. So what you saw in the video is you saw ice heating up. Now, again, not much was going on in the video. You just saw temperatures changing, and you saw ice heating up in the beginning, and then you saw it do something during this flatline portion. But for heating curves, what happens is that when you add heat, I did something. When you add heat, I'm going to put it down here too. I'm going to put in the x-axis heat added. Just as a little indicator of what time means in this case. It also means heat added. So you're adding heat. So as you add more heat to a solid, what happens is it heats up, it changes temperature. All right, so think about what the particles are doing. We talked last week how solids have the least movement of particles, but as you heat up a solid, it starts vibrating more, it starts moving more. And eventually it'll move so much that it'll become a liquid. And that's what's happening during this flatline portion. So again, please jot this down in your notes. In this flatline portion, and again, I got little particles here. So solids have very condensed, very organized particles. In this portion here, what you saw happening was the temperature remained the same from like 3 minutes to 10 minutes. This was when the solid was melting. In other words, the solid was turning into a liquid. All heating curves have this little flat portion for the melting process. Okay? So what happens is that, again, you've all seen this happen before. You take an ice cube out of your freezer, you put it on your table or your kitchen countertop or whatever. What happens is the ice begins to melt. Now, the ice doesn't turn into a higher temperature. The ice remains 0 Celsius, but all that heat that's being added is making the molecules or the particles move faster and move further away from each other, because the substance is turning into a liquid. So instead of the heat being used to increase the temperature, which this part did, now the heat's being used to change the state of matter. In the beginning, it was just heating up. Okay, like when you put your hands under an air drum, like a hand warmer or something, or get a hand warmer for your hands. You are heating up you're warming up your skin. You're not melting your skin. hope not. But this portion, once the solid is to a temperature where it can melt, and that's different for everything, now the extra heat is being used to change the state of matter. If you don't keep adding the heat, it won't eventually all melt. So that's what's going on during this flat portion. It's very weird because a lot of people think that every time you add heat to something, the temperature goes up. Not always, because at this point, it's not going up anymore. It's staying the same until we reach this portion. At this portion, I'm going to write that it is, here we go, 100% melted, right? So all of the, so all the ice, all the solid has melted at this point, and now it can do this other part. So what we're going to do is I'm going to take out some of these boxes also. Come on. Oh my gosh. There you go. So in here, what's happening is now the liquid is heating up. So make sure, again, I know I'm taking a little while going through this, and I would normally do this in class. Sorry about that. So now the liquid is heating up, and again, check out the pictures. So it took all this heat down here for these little solid particles to all of a sudden just become less organized. They're still close, but they're less organized. That's a liquid. So now, heats up until it gets to this point. I didn't mention down here, but this solid is melting, and you can easily check the melting point by looking at the graph there. So 0 degrees Celsius must be the, let me put a little MP, the melting point of this substance, and it's water. So ice melts at 0, water freezes at 0 Celsius. So the liquid's heating up until it reaches this point. At this point, there it is. It's about 100 degrees Celsius. That's when it starts to boil. So when you're putting pasta water on your stove to get it to boil, that is what is happening. So the water gets to 100 degrees Celsius, and then it says, okay, I've reached my boiling point. Now the water is going to start boiling. It's going to start turning into a gas right here. You can also call it vaporization, same thing. At this point, again, notice the flat line. It's a little short on our video, but that's okay. Heat's being used to change the state of matter again. So note that both flatline portions, plateaus you can call them, the heat's being used to change the state of matter. Okay? So you can't get water at over 100 degrees because once it hits 100 degrees, all that water starts to boil. So it starts to become a gas. So if you were to turn the stove off, it doesn't keep boiling because you're not adding any more heat. So if you keep adding heat, then the water will continue to boil until it reaches this last part, which is gas heating up. Now, you don't get this a lot at home because you're not really adding heat to a certain amount of gas, like on your stove. I think the most popular things that a human like you would see, and me at my house, you'd probably see like this portion. You would see like ice taken out of the freezer and melting and then heating up water for pasta and then having the water boil. But this is what's going on for heating curves. It's really just kind of looking at a graph and seeing what the differences are. Now again, it's not always going to be for water. It can be literally for any substance in the universe. Okay? But they all look the same. It's the same idea. But they're going to have different temperatures, different amounts of time with heat added. So when we're back, or when I'm back in class, we'll be looking at trying to read some numbers off of the heating curves. Make sure you get all of this stuff in your notes, and make sure that you add to that discussion post. There's a couple of questions on the discussion post just to see what you know about heating curves. Okay, great.